Full subtractor. Full subtractor is a combinational logic circuit. It is used for the purpose of subtracting two single bit numbers. It also takes into consideration borrow of the lower significant stage. Thus, full subtractor has the ability to perform the subtraction of 3 bits. Full subtractor contains 3 inputs and 2 outputs as shown below. This is a block diagram of full subtractor. It has 3 inputs A, B, borrow in, and 2 outputs in the form of difference and borrowed. Next, we want to see the designing part of full subtractor. Full subtractor is designed in the following steps. Step number 1, identify the input and output variables. By looking at this block diagram, it is very easy to identify the inputs and outputs. So we have input variables A, B and borrow in, and output variables capital D and borrow out, where capital D equal to difference and capital B out equal to borrow. Step number 2, draw the truth table. Truth table has input part and output part. In input part, we have to mention the inputs variable, whereas in output column, we have to mention the output variables. For 3 input variables, total 8 combinations are possible: 000, 001, 010, 011, 100, 101, 110, 111. Now, how to get the entries for these two output function? We have two output functions, borrow and difference. So here, for getting these entries, we have to apply the binary subtraction rules. Already you might have studied in first year about the binary subtraction rules. 0 minus 0, first you need to perform the subtraction between A and B. The output will be subtracted with B in. Alright, so 0 minus 0, output is 0. 0 minus 0, difference 0, borrow 0. 0 minus 0, output 0. 0 minus 1, difference 1, but borrow is 1. Alright, the next 0 minus 1, difference 1, borrow 1. Here difference between 0 minus 1 is 1. Now we have to perform subtraction between output 1 and 0. 1 minus 0, difference 1. Previously we got borrow 1. Alright, the next combination 0 minus 1, output is 1, borrow 1. 1 minus 1, difference 0. The next 1 minus 0, difference 1, borrow 0. 1 minus 0, difference 1, borrow 0. The next 1 minus 0, 1. Then 1 minus 1, difference 0, borrow 0. 1 minus 1, difference 0, borrow 0. 0 minus 0, difference 0, borrow 0. The next 1 minus 1, difference 0, borrow 0. Alright, now this output 0 will be subtracted with 1. 0 minus 1, difference 1, borrow 1. Next, step number 3. Now we want to express each output function in its minimal form. Either you express each output function in SOP form or POS form. Max terms are represented by 0, whereas min terms are represented by 1. Here I would like to express my output functions, in SOP form. So here my focus will be on min terms only. Alright, so here we have to take the help of kmap for getting the minimal expression for each output function. So you need to draw the separate kmap for each output function. So first we will look at the kmap of difference. Alright, so this is a kmap for a difference output function. So total number of cells in kmap is equal to the total number of input combinations. So in input table we have total 8 combinations, therefore we will be having total 8 cells in a kmap. Then we have to place each input combination corresponds to each cell of kmap. So 0 0 1, this input combination, for this particular input combination difference is 1. Alright, so for this respective combination we have to keep 1 in a cell. 0 0 1, 0 0 1. You have to always remember that kmap follows only grade code system. So this is each cell is identified by row and column. Alright, so here we have 0, here 1, 0 0, 0 1, 1 1, 1 0. So accordingly we have to keep the mean terms in this cell. 1 1 1, this combination is also representing mean term in difference column. Alright, so this is the cell number 7, 1 1 1, mean term. Whenever you find such a pattern in your kmap, you can directly express your output function in the form of XORing among the available inputs. Alright, this particular pattern is called checkboard configuration. Next, we want to express output function bin in its SOP form. This is a pictorial view of kmap for output function bin. Total number of cells in a kmap equal to total number of input combination. We have to place this mean term to the respective cell number of a kmap. This is cell number 0 1 3 2 4 5 7 6. So here total 3 pairs are possible. This pair represent the product term a bar dot b. This pair is identified by the row a bar and 2 column b dot b in and b dot b in bar. Between these two we can easily take b as a common. Then we are left with b in plus b in bar. B in plus b in bar is nothing but 1. That's why we have this reduced form of product term a bar dot b. Similarly, we have to express this pair in its product form. So its product form is a bar dot b in, a bar dot b in plus this vertical pair b dot b in. Between a bar dot b in plus b dot b in, we can easily take b in as a common. Step number 4, draw the logic diagram. The implementation of full subtractor using 1 XOR gate, 3 AND gates, 1 NOT gate and 1 OR gate is shown in this diagram. Output function T equal to A XOR B XOR B in, A XOR B XOR B in. Here I have draw this logical diagram for B out by considering the minimal expression as a bar dot b plus a bar dot b in plus b dot b in. So b out equal to a bar dot b. This AND gate is represented by first product term a bar dot b. Second AND gate is represented by the product term a bar dot b in, a bar dot b in. Third AND gate is represented by the product term b dot b in. So this is a complete logical diagram for full subtractor.